Okay, this is a quick introduction to using arrays in Python. First, we'll need to import the libraries. We'll import Numpy as NP. We'll be talking about arrays as Python lists and also Numpy arrays. So arrays can be thought of as single variables that hold multiple values, and you can think of this like a vector that has different components, vx, vy, vz. You can denote this vector by its components, v sub x, v sub y, and v sub k, for example. A column or row vector in linear algebra is an array. We can have two-dimensional arrays. We still use the term array. So we'll refer to array for one-dimensional, two-dimensional, etc. as a generic term for representing collections of numbers. In Excel, you could think of a column of data as an array where each cell is one of the array elements. Python itself refers to arrays usually as lists. So here's the basic syntax to create an array. A equals, we use square brackets. It's a comma separated list between square brackets. So 0.1, comma, 0.02, 0.2, etc. Spaces don't matter. We usually include the spaces here for readability. Once we've defined a basic list or array with square brackets, we can access elements also using square brackets. So now that I have array A, we can type A bracket 0, A bracket 1, etc. to access the elements. The elements are indexed by integers, so this is element 0, element 1, element 2, element 3. So the indexing starts at 0. So here's an example. Creating the array A, a comma-separated list of values between square brackets. And then we can print the whole array. And when we do this, we get the whole array output. And we can also print the elements starting at 0. So A bracket 0, A bracket 1, 2, 3, etc. We can use these values wherever a value would be expected. So A bracket 1 is, in fact, the value that's referred to. So anywhere you expect the thing referred to by A bracket 1, we can use it. So in this case, A bracket 1, let's go back. A bracket 1 was 0.2. So anywhere that you would use a 0.2, this would be valid. So x is, in this case, 0.2. Y is 0.3. And then we can print x and y. So you can assign from the array values. We can also do arithmetic on these, so 1000 times A bracket 2, and then we're going to take this numerical value and assign it to A bracket 2. So whatever used to be an A bracket 2 is now replaced with 1000 times the previous quantity. When we output it, we get 3000. So it used to be 0.3, and we multiply it by 1000 and replace the value, and we get 300. Python lists can store arbitrary types. So we can go B is bracket 5, comma 314, quote Timpanogos sign. So this would be an integer. 5 is an integer. 3.14 is a float. Quote Timpanogos is a string. And np.sign is a function. So they all have different types. And when we print the array B, this list B, we get the different quantities printed out. Because the B bracket 3 is a function, we can use it as a function. So if we do B bracket 3, then this whole quantity highlighted is np.sign, and we can then call the function with pi force. So parentheses np.pi over 4 works just fine. The len function can be used on a list to show how long a list is. So if we have this array, we call len a, and it outputs the length of the list is 4. So it has 4 elements, 0, 1, 2, 3. Starts at 0, ends at 3, but the total length is 4. This is really common in for loops. So if you want to loop over the elements of an array, we can do for I in range, and then len a is the size, so this would be 4, and of course range stops short of the last element. So range len a will be 0, 1, 2, and 3, and then those are sequentially stored in the variable I, and we can use I to access the elements of the array A, so you can see what gets printed here. There's lots more information available for using built-in Python lists, and there's a link here in the posted notes. Okay, so let's look briefly at NumPy arrays. Python lists are nice for numerical work. We pretty much always use NumPy arrays. 90% of the work we do in science, math, and engineering is best done using NumPy arrays. And pretty much all of the above regarding Python lists is the same, except each element needs to be the same type, and we create arrays using a slightly different syntax. And then there's a whole bunch of good lists here for more information about these arrays. Okay, so creating array. We have a couple of useful functions: array, linspace, arange, zeros, ones, and empty. Those are some very important ways to create arrays. So let's try them out. Array, x equals np.array. All of these will be appended with np dot. So we have array as a function, so it has parentheses, and then we give it a Python list, so bracket, comma, separated list of values, and that will create a NumPy array. And then if we print the array, it outputs the result. In this case, the array elements have type integer. We can make a two-dimensional array. In this case, we have an array, the outer brackets, whose elements are also lists. So here we have the first element of the array is a list, and the second element of the array is a list. And this is a comma-separated list of values. In this case, the values are array 1 and array 2, so this will make a two-dimensional array. We access the elements using two indices, so a bracket 1 comma 1, that will get element 4 when we print that, because again it starts at 0, so the 1th row and the 1th column. So the 0th row, this is the 1th row, and then this is column 0 and column 1. So we end up with element 4 when we print A11. We can also, of course, create our array using one-dimensional arrays. So we can create a 2D array, big A, from two one-dimensional arrays, little a and little b. So a comma b, and that works just fine. Okay, the second function, that was the function array. We can make a second function. There is available called Linspace. This is extremely useful. Here we give it a start value, a stop value, and the total number of values. That will include 2 and 8, and all the points created will be uniformly spaced. So 2 to 8 inclusive with 5 total points. So here we get 2, 3.5, 5, 6.5, and 8. 2 and 8 are included, and all points are equally spaced. So Linspace, start, stop, and how many. And then a different function here, we have arange, and this gives us start, stop, and the step size. Arange is the analog of range, and range stops short. So in this case, we won't include, 21 won't be included. And this isn't the number of points, this is the step size that we're going to use. So if you know how many total points you want, use Linspace, and if you know how you want the points to be separated, then use arange. Recognizing again that arange stops short, it doesn't include the last point in the list. Okay, there's a function zeros, np.zeros. 4 will give me an array with 4 zeros in it. That's really useful for initializing an array. That is for making an array that has a given size that we can then fill in the values later. A similar function, np.ones, will create an array of 6 ones in this case. If we want an array of 5s, then we would do x equals 5 times np.ones, and that'll multiply this whole array by 5, each element by 5, so that they all store 5, 5, 5, 5, 5, 5, etc. And empty. So this is also useful for creating an array that has 4 elements, but we don't get to know what it doesn't. The values that the array holds are arbitrary. So you can see the values that were initialized in this case, and that'll vary from time to time. So normally you'll create empty to initialize an array that you then fill in later. It can be faster than zeros because it creates the space but doesn't need to fill in all the values with zeros. We can access elements of the array using square brackets. So just like we did with Python lists, the Numpy arrays work the same way. And we can go backwards as well. So you can have x bracket minus 1 as the last element, x bracket minus 2 is the second to the last element, etc. So you can think of this, if you start at 0 and go backwards, then you're wrapping around to the back of the list by one element. So if we count these, if the element here were indexed 0, 1, 2, 3, 4, 5, 6, then element 0 is the E, element 1 would be the L, E would be 2, M would be 3, and in each case, whenever we move, we increment. So that's 1, 2, 3. If we have minus 1, you're effectively going backwards 1, which goes back to the T. So minus 1 is T. Minus 2 goes back twice. So back once, back twice to index these things. So that's convenient. So here's an example. We have a range 3, 21, 3, print x. So this will have these elements. X bracket 2 gives me 0, 1, 2. It gives me a 9. If we print x, we get these values. You can index the values of x using a list. So if you do x bracket and then provide it a Python list, 1, 5, 3, it will access elements 1, 5, and 3. So this can be done out of order. So if you did 3, 5, 1, then you'd get elements 3, 5, 1 in that order when you index x. You can also store this as an array. So you could do I is np.array154, and then x bracket I will access elements 1, 5, and 4. So you get the results 0, 1 is there, 2, 3, 4, 5 is there, and 0, 1, 2, 3, 4 gives me 15 when I do this kind of indexing. Pretty convenient. And a 2D example again. We can do array slices. We can access multiple elements using the syntax array bracket s colon e. S is the starting index, E is the ending index, and it stops short of the end. So if you put 5 for E, it would go up to and including 4, but not 5. And the S and the E are optional. So if we just do S colon, it'll go from the start all the way to the end of the array. If we just do colon E without an S, then it will assume that S is 0, so it'll start at the beginning. And if we just have a colon without an S or an E, it just means the entire array. So here's an example. Create an array x as np.arange 0 to 11 with step sizes of 1.5. If we do x colon, we get everything. If we go 2 to end, we get from the second element to the very end. So that would be element 0, 1, 2 to the end is what's output for 2 colon. If we do colon minus 2, we get the beginning to one short of the second to the last element. So we'll get these elements, which is what we have. Because again, it stops short of the last one. And the last one shown is minus 2, which is minus 1, minus 2. So we stop short of that, and we get these guys. And then 2 to 5 will give me elements 2, 3, and 4. So 0, 1, 2, 3, and 4. And that's what we get. So you can always do a print statement. When in doubt, do a quick test to see if you get what you expect to get. We can look at the size and shape of an array. np.shape will tell me the shape, it's 2 by 4. np.size will tell me the total number of elements. So this one had 8 total elements in it. So np.size gives me 8. And in this case, the len function tells me the length. The array itself had 2 elements, each of which happened to be an array. So you've got three functions there: shape, size, and len that can be used. For a 1D array, of course, len just gives the number of total elements, like before. Okay, we can do arithmetic and linear algebra. So let's create a simple array A, and then we can do B equals 0.1 times A. This will multiply every element of array A by 0.1 and store the result as B. This is much faster and easier to read than creating an array B and then in a for loop entering all the values. So in both cases we'll get the correct answer, but this is much cleaner both to write and to read. So again, arithmetic, a scalar times an array multiplies every element of the array by the scalar. Same thing happens if we did 0.1 plus A. Every element of A would have 0.1 added to it, and division, etc. A plus B, if we have two different arrays, A and B, it will just add element-wise. So each element of A will be added to each element of B, and the resulting array is returned. If we square each element of the array, we get a new array, and so forth. Okay, we can solve an AX equals B system. If we have a two-dimensional matrix A and a one-dimensional array B, then we can solve AX equals B for X by typing np.linalg.solve A comma B, and the result will be X. And then you can verify that A times X recovers B by using the dot product np.dot A comma B. And this will do a matrix multiplication as opposed to an alternative. Okay, we need to be careful about assignment in Python. If we have x equals np.array and we do y equals x, then we don't have two different arrays. Rather, x and y are both names for the same array object. So if we do y bracket 3 is 44, and then print x and y, both x and y had 44 changed, and that's because x and y refer to the same exact object. You can think of y as being a reference to the object that holds to this array object. If you want them to be totally separate, then you should do y equals x dot copy. Then if we change y3 to be 44, x remains unchanged. So be careful about assignment. If you do a y equals x, realize that it's making another name for your array object and not creating a new object with a different name. So that can be easy to miss. Okay, basic plots. If we import matplotlib.pyplot as PLT and then %matplotlib inline for Jupyter, then if we create two arrays, we can plot the arrays just doing plt.plot x comma y, and that will plot the output. There's some more notes that give you more details on how to do a basic plot. And then a bunch of examples follow, and we can go through those at a later date. So there's a brief introduction to arrays in Python.